Swayam Prabha. Digital India. Educated India.
So, good afternoon again, since the recording is started. So, we will talk about encryption a bit, which I think you have picked up in last few days. We will talk in the context of data encryption. In the morning in the session that Srikanth did, you heard about data in motion, data in use and data at rest. So, this session is primarily on the data at rest part. So, how do you protect the data when it is at rest? So, to begin with, when you have protected your systems with firewalls and all the SCIMs and all of that, security intelligence, you have protected it with firewalls, you have protected it with identity and access, so that no one unintended gets into the system. All of that, when it is there, why do you additionally need to store the data in an encrypted form? You all understand encryption, right? You do not need to go there. There is a slide that talks about it, but we will probably skip it. But why do you really need encryption over and above all those mechanisms that exist to not let an attacker access the system? Why do you think? Can you think of it? So, that is about confidentiality. You heard about the CIA triad? Yeah. So, it is the C triad and it is about making C of the triad, and it is about making the information invisible or not. You cannot read the information or access the information without knowing the encryption keys, right? And that is how you protect the information. Even if someone gets into the system, if the person does not have the keys, the person will not be able to take the data away and use it. He may be able to take the data away, but there is no way you could use it. That is what the claim cryptography or encryption has, but there are ways to crack it. You all know about it, right? You know what crypto analysis is, right? You know difference between what is cryptology? Cryptology is combination of cryptography and crypto analysis. When you do analysis, you are actually trying to crack the system. When you do cryptography, you are actually encrypt the system such that it is not accessible to people. So, with that background, let us jump into the topic. We are going to talk about data at rest. So, data at rest exists in different forms. Take a look at this slide. You will see data exists in databases, right? So, you could protect your data by encrypting the database, that is database encryption. Data could exist in files, in your file systems. So, you could encrypt the files at a file level, right? And then data could exist in, it could be in binary format, it could be in a block format, it could be just a big chunk of data, which is a disk system, right? It could be the entire disk, and you could encrypt at entire disk itself. Have you heard of your entire disk getting encrypted? There are tools that which actually can encrypt your entire mobile data. It can encrypt an entire hard disk or your pen drive, so that unless you authenticate and provide the keys, it does not let you actually access it, right. So, that is about encryption at different levels, and it comes at different granularity, right. So, databases can be encrypted at a level, let us say you could encrypt a certain column only. So, let us say in an employee database you could just encrypt the salary part, and someone who provides the keys can only view it, let us say manager. right, or the HR team can only view it. That is an example of granular encryption, and then you could also encrypt the entire table space. So that this customer who has his data. So, in multi-tenancy we talked about how one customer can access the data of what they own, they cannot access some other customer's data, right. So, in that case this customer could have their own keys which actually encrypts their table spaces. Typically you use table spaces to separate multi-tenant data, right. That is one of the way to separate. Multi-tenancy can be achieved in different ways. You could store all the data in one table and then say there is a column which says customer number, and that way you can use a where clause to separate out the data of one customer. That is one level of achieving multi-tenancy and separation of data, but that is co-locating entire data in one table, right. That is one way of doing it. The other way is you create tables and you create separate tables with the table names being different. Let us say the customer ID is there in every table names, right. That is another way of separating tenant data. The third way is you separate the table space. The fourth way is you have a separate partition, volume, what you call. In Oracle, I think it is volume. And then fourth way, another way is you have a different database server. There could be different servers serving different customers. And then the fifth way is actually different VM, virtual machine itself. So, entire application could be different. So, these are different levels of multi-tenancy, and you could use different levels of encryption to actually separate or rather isolate the data and make it inaccessible for one customer to access the data from the other customer, right. That is one of the application of how you can use a granular level of encryption to make sure that the right level of access is given to the different tenants that are using the data. Now, let us switch to file based or file system encryption, right. It could be native encryption, like for example, the file system itself has utilities to encrypt the entire file system. The operating system has it, or it could be agent based. So, there could be an agent which actually traps every request that comes to the file system and encrypts that file system, such that the agent actually controls whom to give the access and whom to not give the access, right. So, that is file system, and that is fairly simple to visualize or think of. The last comes the disk encryption, which is one of the oldest form, where the entire disk gets encrypted, and you could do volumes, you could do partitions, and selectively you can encrypt chunks of data, and you could use separate different keys to encrypt different parts of the disks. Different volumes could be encrypted using different keys, right. So, that is how the data encryption is at a different level. So, you have learned this, I am not going to repeat it, but you recognize this, right. What is symmetric encryption? What is the key of symmetric encryption? What is the most important factor of symmetric encryption? There is no public private key, there is only one key. There is one key, the same key is used for encryption and the same is used for decryption. The algorithm is public, just remember that. Those are fundamentals. In any crypto system, the algorithms are public. It is the key that is secret, and it has to be with the right people to give those people the access to that data, right. And if someone gets hold of your keys and they know the algorithm, you are doomed, right, you are gone. So, the entire crypto analysis is focused on determining what the key is, right. And what are the common techniques? Have you learned the techniques for crypto analysis? What is the most popular and known or known technique for crypto analysis. Substitution is a cipher. How do you crack that cipher? Brute force. Someone said that. Who said that? Right. So, brute force actually is the technique to crack the key. What does it mean? You actually attempt multiple times and try to guess all possible combinations of the keys. You try to use through that algorithm and find what the clear text is. So, the crypto analysis goal is you are given an algorithm and you are given the plain text, you are given the cipher text and you have to find what the plain text is. That is the common goal. That is what sometimes it is not to find the plain text, it is to find what the key is, so that you can decrypt the entire cipher text. So, you have heard of the different techniques, known plain text, known cipher text, these techniques, frequency letter attack. Have you learned these attack techniques? If not, then you should probably go back and look up what are the different crypto analysis techniques to actually crack, let us say, a given crypto system. So, letter frequency attack is a attack that is used to crack a substitution cipher, correct. So, letter frequency attack says you have, let us say, in the language English, what is the most commonly occurring letter? Correct, E, and what is the next? T, correct. So, E and T. So, you try to find in the cipher text what are the more frequently occurring and try to do the modulo arithmetic to find what is the key. You have heard of modulo arithmetic. There is a lot of math involved when you are learning security and cryptography. You need to learn modulo arithmetic to be able to know how most of the ciphers work. You need to understand those mathematical concepts. Okay. So, coming back to the topic, those are symmetric encryption algorithms, where the encryption and decryption is achieved using the same key. Now, how does the key gets transferred? Sometimes the user who is trying to encrypt may not be the same user who is trying to decrypt. It could be different users. So, I am sending the data to you and you need to decrypt it. In that case, you need to know the key. How am I going to transfer it to you? I can tell it to your phone. So, what are the techniques? So, there is a complete subject or a topic on key distribution. How to distribute the key? You have heard of Kerberos? Right. So, basically these techniques are about key distribution. How to manage distribution of keys such that you can share the keys with the trusted people in the network, or you find a channel that is trustworthy to transfer the key. Now, the third approach to it is public cryptography. Right? What is public cryptography? That is asymmetric encryption. Two keys are used. So, you have a public key and you have a private key, and you, when you are sending, you use the public key, and then it is irreversible. Remember that, irreversible. Once the data is encrypted using the public key, you cannot decrypt it using the same public key. It is only the private key that can be used to decrypt that data. So, it is one way, irreversible, and then private key can be used to decrypt the data. And there are common techniques like RSA and ECC. You heard of these? Yes. Right. So, they are used to, they are public cryptography. They are public cryptography. Now, I will tell you some practical differences between asymmetric and symmetric algorithms and public private cryptography, or rather symmetric and asymmetric. I won't call private cryptography. There is public cryptography and there is symmetric. So, symmetric algorithms are fairly strong as compared to public algorithms. There is a reason for that. The complexity involved in public cryptography or the asymmetric encryptions is fairly high, and as a result you can't use the strength bits number of bits that are used as much as you can use it for the private or rather the symmetric cryptography, and hence it is relatively easier to implement symmetric over asymmetric, and it is also faster. Symmetric is much faster than asymmetric, and this has lot of implications to what can be cracked, what can be analyzed, and what is at risk, right. So, we will talk a bit about that in slides down. So, here it is, just now what I talked about, right. This is a comparison of what is the key length and what is the equivalent of that, as in to achieve that level of security, what is it that you need in symmetric and asymmetric different algorithms. So, we have comparison of AES, RSA and ECC, right. So, as you can see 128 bit AES, you know AES, right. AES is a block cipher, it is a block cipher, it is advanced encryption standard. So, 128 bit of AES is equivalent to 3072 bit of asymmetric key, which is RSA, and similarly it is twice in the ECC elliptical. So, you can see you can achieve much more robust or secure system using symmetric key as compared to the asymmetric key algorithms, but the symmetric key algorithms have the problem of not being able to manage the transfer of keys, right. So, you cannot use it where the user who is trying to encrypt is different from the user who is trying to decrypt very easily. You will have to transport the key from the user who is encrypted to the user who wants to decrypt. So, what is the solution? Can't we use both? Do you know where both are used? Here is an example, SSL. So, what does SSL do? Everyone knows SSL. So, have you done programming? Have you started doing socket programming? So, in sockets what do? You establish a SSL connection, right, and your C or C libraries offer you that secure libraries that allow you to establish a secure connection over sockets. And what happens over there is essentially you are trying to use symmetric and asymmetric algorithms both to secure the transfer of the symmetric key to the other user, right, using the public cryptography. So, you use public cryptography to transfer the keys, but what you are transferring is a key which is a symmetric key. So, you are having power of both, right. You are able to use the power of both these, that is a symmetric and asymmetric. So, I am not going to walk you through the entire flow here. These slides are going to be available to you, but what essentially was happening here is you have one user who wants to send, uses public cryptography or asymmetric algorithm to send the asymmetric keys across to the other user. Send the symmetric keys to the other user, right. That is what is happening here. we have tried to set the base for the rest of the session by establishing what symmetric, asymmetric, key strength, what are the challenges in each of these techniques and how both can be used to achieve an example of that. So, any questions so far on this? No questions? Okay. So, let us move on. So, it is very important that you, when you are using these techniques, the keys are secured, right. And so, since the keys are so important that it actually everything, entire system's security hinges on to how you manage the keys, because if the keys are lost, your data is destroyed. If your keys are stolen, your data is stolen, right. So, it is very important that you manage your keys very well, and for that you have an entire protocol and a server or a system actually that is built or created to manage the keys. Is a key management server. So, what is the function of this key management server? You are a client wanting to encrypt your data, right. So, what you do is you say I need keys. You do not create your own keys, you ask the key management server to generate a key for you. You get those keys over that SSL connection what I just described. You encrypt your data and just get rid of the keys. You do not need the keys, do not store the keys. You got my point? So, if someone gets hold of the data, what does he or she needs to do? Needs to decrypt. Where can the person get the keys? Key management server. So, the person has to be authenticated to that key management server to actually be able to access this data, to decrypt the data. So, that is the concept of key manager, right. Key management server. So, stepping back a bit, right. How was this when there was no key management server? The keys were stored locally, and again they were encrypted, and they were encrypted using Java libraries. So, how many of you heard JCE? So, Java crypto, I do not remember the full form of that acronym, but it is basically the libraries that allow you to use the Java library that allow you to do encryption, right. So, Java libraries, so encryption is done by the Java libraries, but then the keys are stored outside in a key store. So, what we have is a Java key store, JKS. So, those of you who have built applications and want to encrypt something, what they would do is they will generate the key. There are Java programs that allow you to create the keys, encrypt the data, and then store the key in the Java key store, right. And then when you authenticate yourself, obviously you are authenticated to the application, you can actually access the same Java key store, retrieve the keys and decrypt the data that you have stored in your Java application. It is a fun application to create, try it out. Just read up a bit on JCE and try to encrypt your, see it could be a small project, how to use JKS. It is actually not even a project, it is a program. You will get sample programs to do this on the web. So, most application developers who wish to encrypt the data need this JKS, right, when they are doing locally. Now, when there is JKS, why do you need a separate server, key management server? That is further strengthening the security. If you are storing it locally, suppose it gets destroyed, your data is gone, right. So, JKS is not an ideal way to store your encryption keys. You would want to store it somewhere such that you can retrieve it and you can actually use it whenever you want, right. So, that is where this key management server comes into play, and key management servers actually have a special protocol using which they interact with the clients. When I say client, it is the self encrypting devices or this Java programs that actually are trying to get the keys, encrypt, and then get the keys, decrypt, and so on, right. That is the operation. So, you have a client actually who will be responsible for accessing the server for key management server and get the keys and use them for encryption. So, that is the function or a model of how a client server interacts for the keys that are used for encryption, right. So, there is a entire protocol which is key management interoperability protocol that is in existence. It is a standard body which actually governs or helps all the devices that are trying to access a key management server and how the server responds. So, it is a protocol by itself. You can search for it. You can search for KMIP and you will get material around it. You will see. So, KMIP is a standard. So, KMIP standard, you will get what exactly it is, right. Similarly, the keys could be stored like KMIP servers store the keys can also be stored on HSM appliances. So, what is HSM? Srikant actually in the morning he touched briefly on what HSM, right. So, hardware security module allows you to store the keys in the hardware such that keys do not leave the HSM. So, when HSM is there, you do not need typically you would not need a KMIP server, but what happens is your data comes to the HSM, it gets encrypted and sent back. So, when the data is huge, you cannot use something like HSM, because you can't be sending the entire data to HSM and get it encrypted and get it back, right. That is not a practical thing to do. So, typically what you would do is you would have keys that you are getting from the key management server. You will encrypt those keys using what's in using. So, key encrypting key. So, what I do is I have two levels of encryption. I use a key that I have a key, I use that to open the database, but how can I access the key? That key itself can also be encrypted using the key that is stored in HSM. That is the concept behind HSM and why you need HSMs, right, and how typically HSMs get used. So, HSMs typically are used to encrypt the key and not the data. The key in turn is then used to encrypt the data, right. So, KMIP servers and HSM appliances are key management interfaces. Similarly, you could have a cloud KMS. So, cloud KMS allows you to store the keys on the cloud. It is nothing but whatever you found on prem could be kept on the cloud. So, example of cloud KMS is Key Protect, that is IBM Key Protect, which can be used to encrypt data that you are trying to store on the cloud. Typically, it is the application who would want to access these cloud KMS systems, right. Applications who wish to encrypt. Similarly, Amazon have their own KMS, key management implementation. Google has their own key management implementation. Azure has a different form of key management. Everyone has a key management interface that is required for encrypting and decrypting your data, right. Okay, so, here is an example, very crowded architecture, but I will try and simplify it by pointing you to the very important parts of this. So, here what the objective of this system is to encrypt the database that is stored in DB2, the data that is stored in DB2. DB2 is IBM's relational database, It is an IBM's relational database system that is used to store relational data. And this system, what is depicted on this diagram, actually allows you to encrypt the data that is getting stored natively on the database, right. So, it achieves native encryption for the DB2 server, DB2 system, right. So, how does it achieve it? You have a key store where you are storing your keys locally, and you are trying to encrypt the data that is stored in the database. What happens is, there is a client that sits here, it tries to reach out to the key management server. You see KMIP server here, the one that I was referring to. It accesses the key management server, it gets the keys from there, use that key to encrypt the data and push it back into the database, right. There is a concept of master key. The master key is the key that is used to encrypt the individual data encryption keys, right. So, individual data encryption keys are stored in the key store, but then those keys are not stored as is, they are encrypted using the master key, and that master key is obtained from the key management server. So, why do we do this double business? Why do we need master key and then key store? It solves a typical peculiar problem that I talked about just now. You can't transfer the entire data to the key management server, or you can't be going every time you want to encrypt a small row level data, or let us say one row in the system. If you want to encrypt, you can't be going back to the key management server on the wire and get the keys to decrypt it or encrypt it. It is very expensive to do that. So, how do you do that? You have local keys. You use those local keys to encrypt, decrypt, and that operation is pretty fast. But then that local key is at the time of the startup actually is encrypted and decrypted using a master key that is stored on the KMIP server, right. So, this is just a little bit this is a little different implementation. You will see that there is an HSM server used here instead of a key management server. There is no different, right. So, I am not going to explain this, but this is basically, instead of the key management server, you are using a HSM server. So, this is just a slide to help you understand how encryption of the data that is sent to the cloud can be achieved, right. So, there is a product called multi-cloud data encryption. It is again an IBM product. By the way, there is a KMIP server which is again an IBM product called SKLM, Security Key Lifecycle Manager. It allows you to store the or manage the life cycle of the keys, right. So, multi-cloud data encryption is again a product that allows you to use agents to encrypt the data, but then these agents are at the back end getting the keys from a key management server or an HSM, right. So, what the agent does is, there is a MDE server, that MDE server actually deploys an agent on the endpoint, which could be a cloud system, and that agent actually is doing the real encryption magic, but then it is obtaining the policy and keys from the key manager. Okay. So, stepping back, we talked about encryption, we talked about database encryption, we talked about file level encryption. When do you use what, and why do you use one of those or both of those? Based on what I just talked so far, I think you should be able to easily guess why there is a pyramid. The most frequently occurring word here is granular, right. So, granularity increases as you go up in the pyramid, right. At the bottom of the pyramid, entire 100% data is encrypted using one key. You get one key, you can decrypt the entire data. So, that leaves the data vulnerable, right? It can be entire data is accessible to everyone. That is why you need another level of encryption, which actually encrypts for smaller subsets, and that is when the next level comes in. So, file systems, the next level comes in, which is the database systems, right, at a database level, and then the app level. But then there are disadvantages of each. Someone achieves a lot of granularity, but what are you losing there? The standards, the complexity. The app based encryption may not be a standard encryption. You can, as a programmer, write whatever you want to encrypt it. You can use different mechanisms to encrypt it. That is not the case with agent based or file based or database. You have to use standard techniques, and there is more transparency in that type of encryption, although the keys are secret, right. So, as I mean, that is the point is explained here, is the granularity, the complexity, those are the ones, those are the trade-offs here. Okay. So, now I am switching the topic a bit to something a little more interesting, so that you stay awake. So, we will talk a bit about quantum. How many of you heard of quantum computers? You are all computer science graduates, right? You should be dreaming of working on these computers, right, on these computers, because this is another 10 years down the line, when 10 years, 20 years down the line, when you will probably be sitting in this chair and addressing an audience like this, right. I have been in times when I have had a PC and we used a floppy drive, floppy disk, which was 1.44 MB and the 64 MB. It is not GB. We tend to say GB, right? It is not GB, it is MB. That is the time when I started development and programming, right. So, this quantum is again a little far away, but there is a lot of research happening in different corners of the world. IBM has started its journey, and we will talk a bit about that in coming slides, but the concept here is that you have the use of qubits, which actually is not, bits is binary digits, right. Everyone knows what bits is, right, binary digits, it is 2, 0 or 1. Qubits is, it could be multiple, the same one, I will not call it a bit, it is a qubit, could have more than one interpretation, right. It could convey more information than just those 2 bits, the same qubit, and it is shrinking day by day. At the same time, the amount of information that can be stored and can be processed is growing, right. It is not yet commercially viable, but it will be someday. So, what is the key, what is the concept is, because there are multiple interpretations of the same bit, you can store more and you can process more, and hence you can do more, right. You can compute much faster, and you can do at a larger scale. You can, huge data can be processed at the same time. So, those are the key I would say takeaways or the drivers for quantum, or what quantum is driving. And as a result, what is the risk that it brings in? It, like there is advantage, you can solve many complex problems which are need huge computing power. There are problems that it is likely to create. We talked about brute force, right? What is brute force? Trying all the possibilities. So, when you use 256 bit AES, do you know how many possibilities you have to try Can any computer do that in a reasonable amount of time? No. That is why AES 256 is regarded as standard, or rather more powerful, and to date, as of today, even a quantum computer cannot crack it. That is the power of AES 256. There are many other intricate details of why AES is much more robust. We will not get into that. You will have to understand the depth of the mathematics and the cryptography involved in it. But for a layman, or I will not call you layman, but for someone who does not understand the math and crypto behind it, it is good enough for you to understand that AES 256 is strong enough such that a quantum computer, when it applies brute force, cannot crack it, right, and that is why it is called quantum proof as of today. So, what else is quantum proof and what else is not? Most public crypto systems are not quantum proof. So, you have to find a different way to transfer keys, because today with SSL you are trying to use asymmetric algorithms like RSA or ECC to transfer these symmetric keys, which is unsafe, because if someone can know the asymmetric and crack asymmetric, and you are sending using asymmetric and symmetric key, your keys can be stolen, right, on the flight. Someone who has established an SSL connection using that asymmetric algorithm believes that my keys are going to be safely landing to you without getting intercepted. But someone with a quantum computer, if he or she intercepts it, can actually get the keys, right. So, your SSL session is at risk, SSL is at risk. Your data that is stored in the disk using a symmetric key, if you are going to access it again, that is safe, that is not a problem. But data that is sent over the wire, so why is SSL established? Okay, I should have explained a bit about SSL. So, you transfer the keys to the other user and then you encrypt using that symmetric key and send it over the same wire using the public. You do not need to actually encrypt it. You do not. So, when you establish the connection, you have transferred the keys. After that, when you send the data, it is a different socket. You do not really use public cryptography for that. You use only symmetric algorithm, because the other person has the keys. You have transferred it in the previous session, right. So, as a result, what happens is, if your first connection session where you are establishing the initial contact, where you are transferring the symmetric key, if that is hacked by a quantum computer, then your symmetric key is stolen. Anything that you send after that can be intercepted and interpreted very easily. Are you getting the point? These are base concepts, right? Do not go wrong here. If you are not getting this, you are in trouble. So, get this right. What is public? Why is it at risk? What is symmetric? And how is it at risk? Okay. So, the claim is that the Shor's algorithm, there are two algorithms, Shor's and is the other one Grover's. According to them, there is an exponential improvement in brute force, and according to Grover, it is quadratic improvement. So, they will get you closer to cracking the keys. So, this is the same point that I made in these two slides. If the keys are intercepted, if the public cryptography, or if your asymmetric transfer is cracked and they gain access to your symmetric key, your data that is transferred will be at risk. There is another interesting fact that is mentioned here. Suppose today there is no quantum computer, but you get hold of that key or that session, you intercept that session and get that data, that packet. You are not able to use quantum computer to crack and find the symmetric, but you keep it with you, and then you also intercept all the data and keep it. And suppose after 5 years, when there are commercially available quantum services or quantum computers, you can throw this back to them, and whatever you have intercepted 5 years ago will get exposed or will be decrypted, right. So, it is not, you can't be closing your eyes and saying today there are no quantum computers, I can send whatever I want using public cryptography, because what is sent could be intercepted today, and there is information which could be still relevant after 5 years and is still secret. Even after 5 years, it is equally secret or more important that it does not get divulged, right. So, that is the another risk of quantum that imposes on the data. So, you may not cause damage today, but you could cause damage after 5 years when you get powerful enough computers to crack it. Get my point? So, what is the work? This is just some updates on what is happening. Lattice cryptography, have you heard of it? Must have just briefly heard about it. So, like your elliptic, there is lattice cryptography. It is another technique. It uses matrices to actually do all that juggling of data. You heard how the data is juggled in DES and AES, right? Yeah. It goes through your transformations, which is you do what you call diffusion and what's the other thing? You substitution and diffusion, right? You do two different what do you say, two different operations to actually get to the next level, and then you do it repeatedly. After 3 rounds, you actually, after 10 rounds, you actually make it completely proof, right. You have to go through 10 rounds of those substitution and diffusion to actually make it completely secure. So, similarly, lattice cryptography also has similar techniques or similar algorithms that allow you to encrypt, and that is actually the algorithm along with others that is being proposed to NIST. How many of you heard of NIST? Well, if you are in crypto and security business, you need to know what NIST is. National Institute of Standards Technology, but it has standards that are relevant to security, right. And it is basically an American standard, and there are a lot of derivations of that other countries had adopted, and it is basically a standard body which actually invites proposals. So, the AES was standardized or proposed by NIST. They invite proposals, they shortlist, and then they select, and they say this is the winner, and that is used as a standard across entire world for exchange of information. So, NIST actually has proposals for PQC standardization. Already they have invited. IBM is one of the companies that has submitted proposals for at NIST, and I think it will be another couple of years for them. The proposals are just in. The last dates for submitting proposals has just gone past a few months ago, and now they are reviewing those proposals. While there are no quantum computers, or while there is a risk looming, what are the few things that you could do to secure your data? Use AES, triple DES, as far as possible, use as long keys as possible. But remember, as the key size grows, it has performance impacts. So, you have to use the right key size. But then there is no escape to AES 256 you want to, if you want to make it quantum proof, right. On asymmetric, minimize the use, as far as possible do not use asymmetric, and whenever the new algorithms are available, you could start using those new algorithms for you have to transition to those for the asymmetric algorithms. Have you heard of hash algorithms? So, you have heard of all these, right? Hash, signatures, certificates, you must have gone through that in your course. So, hash, again, longer the output is required, longer output is required. So, if you try to keep it with a smaller size of output in the hash, there is a higher chance of collision and you can detect or crack it easily. So, the longer the hash, the difficult it is to crack it. So, that is the point we make here. So, these are few references for quantum cryptography and NIST on quantum, and that is it. So, I am done with the session on encryption part. I am going to continue on the secure engineering a bit if you are interested, but I am done with the session that I was planning for. So, if you use 128 bit security on a standard computer, which is as of today, see, security level is the strength of security. How strong is the security that you are using? That it is a metric to define how strong is the security that you are using, security level. You get that point? What is security level? When I say my security level is 128 bit, my algorithm is 128 bit strong. If it is 64 bit, it is weaker. So, when we say AES 128, it is 128 bit strong, right. On a standard computer, it is 128 bit strong, but that same algorithm, that strength of that algorithm becomes half when it is 64 bit. So, strength of an algorithm on a standard computer, classical computer, how many bits do we have today? What is the common architecture? How many bits? 32? 64. So, 32 bit is gone now. There is, you have to actually have a compatibility with 32 bit. Standard applications and use 64 bit, right. For a standard 64 bit computer, which is most of your laptops and servers all over, the security level or strength of a AES 128 is 128. Actually, that is where it gets its name. But if you go to a quantum computer and say, I am 128 bit strong algorithm, quantum would say, no, you are 64, because you are 128 bit strong on the classical computer. On quantum, you are only 64 bit. It will always reduce. I will not say always reduce. Actually, there are a few things that the quantum computers cannot do as good as classical, and you can read about that. Actually, if you go and read a few YouTube, if you listen to a few YouTube videos on what quantum computer is, there are some problems that the classical computers can solve better than the quantum, right. So, you can't always say that it will reduce. There could be some problems that can still be difficult to crack on quantum. Okay. So, with that I will close this session.